Hi everyone, Lloyd Rieber here again with my next presentation of the course Statistics and Education for Mere Mortals. In this presentation I'll introduce you to our next topic, correlational statistics. Now up to this point we've only been exploring data sets dealing with a single variable, also known as univariate distributions. Now we're going to turn our attention to data sets involving two variables that are paired in some way. The formal statistical name for these are bivariate distributions. The question we will be asking is whether or not there is a relationship between the two variables, and if so, what kind of relationship is it, and how strong is the relationship? For example, I'd like to think that people who are from Pittsburgh are smart, funny, and good-looking. Personally, I'd be happy with just one of these. A more serious example would be, do students who study the most get better grades? Or is there a relationship between the amount of education one gets and income? But interpreting these relationships correctly can be tricky, as I will point out. I'll also introduce how to calculate a correlation in order to get you ready for our next Excel video tutorial. Okay, let's get started. Knowing some statistical principles can be very empowering and also be very useful in everyday life. For example, how many of us have heard a campaign promise similar to this? If elected, I pledge that every child's math and reading test scores will be above average. Well, if you know anything about averages, you know that that is mathematically impossible. We can't all be above average because of how averages are computed. As another example, imagine going to the doctor and saying, "Doctor, I want to be taller," and the doctor offering this advice: "Son, take up basketball." Well, this is meant to be a funny example because even though we know that the best basketball players happen to be the tallest, we would not expect to grow if we actually take up the sport. However, these are exactly the kinds of traps people can fall into when they're trying to interpret correlations. Or how about if I say I think reading ability depends on how big your feet are? Would you agree with this? Now at first you're going to say or think, this is ridiculous. But what if I go into an elementary school and collect some data, and it turns out that it does indeed show a relationship? Well, if you think about it, those students who are in kindergarten are going to have smaller feet than students that are in 5th or 6th grade, and it will also show that the kindergartners and the first graders, that their reading ability is not as well developed or not as high as the students in 5th or 6th grade. So you would be quick to point out that higher reading ability is really caused by other factors, such as maturity, or amount of schooling, or amount of reading instruction. So correlations or relationships can appear between variables that you least suspect, but understanding what's going on, again, can be very tricky. So, similar to the statistical principle that we all can't be above average, another important principle is correlation does not imply causation. And here is a good quote that I think really makes this point well. A high correlation does not give you the kind of evidence that allows you to make cause and effect statements. Therefore, don't do it, ever. A very good historical example to consider is the link between smoking and lung cancer. Early on in the history of lung cancer research, the research that had been conducted was all correlational, and there was a very strong correlation between smoking and lung cancer. But only given that evidence, one could not make the causal link that smoking was causing cancer. And apparently the tobacco companies were very quick to point out this statistical principle. And it was only when more research was done that was experimental or inferential in nature was done that the causal link, the cause and effect link, that smoking causes cancer or is a leading contributor to causing lung cancer, that the link was established. Any presentation of correlation must acknowledge the contributions of some of the key historical figures, and that would be Sir Francis Galton and Carl Pearson. One thing I like about the history of correlation is the fact that it really started with the use of visualization as an aid to problem solving, and that's something I'm actually quite interested in. And Galton was interested in relationships among variables, and one of the classic examples was the relationship between the height of parents and their offspring. These kinds of visualizations are called scatter plots, and they're really quite clever. So here is a small portion of the data from a classic 1903 study that Galton did comparing the heights of fathers and their daughters. To build a scatter plot, you assign one of the variables to the x-axis and the other variable to the y-axis. In this case, father's heights on the x and the daughter's heights on the y. So I would go over 69 and up 62 and draw a point or an x. Then go over 68 and up 65 and put another dot or an x, and so on. And as you plot lots of points, you look to see what kind of shape begins to emerge. For example, even in this very limited data set, I begin to see a shape of a trend that is going from left to right and kind of moving upward. Next, you look to see if it's possible to draw a line through that shape right through the middle of whatever that trend happens to be. For example, I can see myself being able to draw a line like so, and you see that the line is moving upward from left to right. Now, as it turns out, this is called a regression line, and that slope of that line is going to give me some understanding of the relationship between these variables. A line that slopes upward from left to right, like you see here, would be considered a positive correlation, meaning that as the father's heights increase, so does the tendency of the daughter's heights to increase. Now, a good question is, how strong is that relationship? According to the 1903 study, the correlation of this relationship, as given by the statistic R, was 0.513. Now, we'll consider what that means shortly. Now, obviously, looking at a data set that only consists of 6 pairs of data points isn't very good. So let's take a look at some other data sets that have lots of points. Well, here we have a scatter plot with a lot more points. This particular example and the ones that follow come from a really nice website that I found that gives you opportunities to look at a scatter plot and try to estimate what the correlation is. As you can see, I correctly estimated it to be 0.73, positive 0.73. And I'll share this website with you in the resources section of the course so you can have as much practice as you want trying to estimate correlations based on the scatter plots also. So a really good technique is to draw the perimeter or the envelope that would go around this set of points. And that's my best attempt. And you can kind of see that cigar or pickle shape, again, going from left to right in a upward fashion. Now the next step is to draw a line that divides that in half as best as you can. I think that's pretty good. And that line, also called the regression line, is on a slope that again gives you a nice visual of the correlation, if there is one, and the strength of the correlation. And what's important to remember is that correlations only range from -1 to +1. They can't be any higher, they can't be any lower. So a correlation of 0.73 is a rather strong correlation, as you can see. As values on the x-axis get bigger, the values on the y-axis also tend to get bigger, and that's a pretty tight band of data points going, again, left to right in an upward fashion. Now, it's very important for me to point out something. All of these examples that I've taken from this website use an x-axis that has a different scale than the y-axis. What I mean by that is if you look down here between 20 and 25, and between here and 20 and 25, you see that the length of that line is different for those two axes. So that's a little unfortunate that the scales are different. If you had a correlation, a positive correlation that was a perfect +1, that line should go on a 45-degree angle, but that assumes that the two scales are going to be identical. So kind of keep that in mind as you see the next few examples. Here's another example. So I again will draw the envelope around the set of points, and you see this time it's a little wider or a little fatter. And also when I go and draw the regression line, it's again a positive correlation, but it's not quite as strong as the last one. But it again shows a good example of a positive correlation. As you can see, the correct estimate here is 0.61. Now consider this example. As I draw the envelope around it, and as I draw the regression line. This is a good example of a negative correlation because the line is going in a downward fashion from left to right. So as the values on the x-axis get bigger, the values on the y-axis get smaller. And the estimate of this correlation is negative 0.48. Now consider this example. I'll again do my best to draw the envelope around it. Notice I do ignore some of those points way at the edges. They're outliers. Now, what to make of it? Where would I draw my regression line? As I look at it, I really can't decide where to draw the line. I don't see a trend. So this is a good example of either a very weak correlation or a non-existent correlation. I don't see a relationship between the two variables. The correct estimate, as you can see, is a positive 0.16. But visually, I would say that there is no correlation or no relationship between these two variables. So a correlation of 0 means that there is no relationship between the two variables. In the last part of this presentation, I want to orient you to how to compute R. Now, the statistic R has a more formal name. It is the Pearson product moment correlational coefficient. This statistic is often referred to simply as a Pearson R, named in honor of Carl Pearson, who we learned about a little bit earlier. There are many ways to compute R. In fact, many textbooks will show you what they consider to be an easier way to do the computation, assuming you're only using a calculator. But as you know, we are using Excel, and we're going to use a formula that I think not only explains or helps us to understand what this statistic R is all about, I think you're going to also find it to be very easy to compute given what we've done so far with Excel. Now, a word of warning to anyone who jumped ahead. If you have not completed the other videos, you will not probably understand what we're going to talk about in the next few minutes here in this presentation. If you have completed all of the other videos, especially the Excel video tutorials, I'm actually hoping you're getting rather excited at this point. And you're saying to yourself, I think I know exactly what to do. It looks like what I'm supposed to do is multiply two sets of z-scores, add them all up, and then divide that total sum by n. Now you might be wondering what n is based on. As it turns out, n is simply the total number of pairs of scores. And the other reason you should be excited is that you know something about a z-score. And if you don't know what a z-score is, I suggest you go back, watch the videos, and do the work that's necessary so that you do understand what a z-score is. Then, at this point, what we're about to talk about is going to make a lot of sense. Let's consider this example that was actually done in Excel. You can see I have two sets of scores, one in green and one in light blue, and I show the raw scores and the z-scores for each set of scores. Now notice that the scores are exactly the same in both sets. This guarantees you're going to have a perfect positive correlation of 1.00. I'm only doing this to illustrate the computational principles that are going on here. Now remember just how special a z-score is. Remember that a z-score contains information about central tendency and variability. All right, let's consider the first score. We have a 20 with a z-score of negative 1.39. And so we have two z-scores of negative 1.39. That makes sense. The mean of the data sets are both 50, so a 20 is well below that, so it's a negative number, and we can see it's, negative 1.39 standard deviations below the mean. So the formula, which I have over here for us to consider, keep that in mind, is that we need to multiply the z-scores. So if I start with the first two set of z-scores, a negative times a negative is going to give me a positive. Now that's rather interesting, isn't it? Because if you look down at the 80, it is also 1.39 standard deviations. However, it is above the mean. 80, of course, is quite a bit above a mean of 50. So I'm also going to get a positive number. Well, this makes sense in terms of correlation in that a low score on the x-axis means a low score on the y-axis. So a high score on the x-axis and a high score on the y-axis combined means we have a very strong correlation. So it makes sense that I'm going to get numbers that are going to increase the numerator of this equation. And indeed, as I look here, every time I have a negative z-score over here, I have a negative over here. So when I multiply them together, I'm always going to get a positive. So the calculation is to sum all those up, and you'll see when I do that, I get a sum of 6.00. And the formula says then I need to divide all of that by n, and n refers to the pairs of numbers. So I have over here that we have 6 pairs of numbers. So 6.00 divided by 6 gives me a correlation, a perfect positive correlation of 1.00. Now if it was higher than 1.00, that would be one of those mathematical checks to tell me I did something wrong. It cannot go above a positive 1.0 nor below negative 1.00. Okay, let's consider this example of a negative correlation, and once again it is a perfectly negative correlation. The answer, as you can see, is going to come to negative 1.00. Well, all I've done is, if you look in set 1 scores, I've turned these upside down. So now I have 80 going all the way down to 20. So let's take a look and see what this does. Now once again, the z-score of 80 is a positive 1.39. So now I have a positive 139 multiplied by a negative 1.39. So a positive times a negative is going to give me a negative. So I have a negative 1.93 when I multiply those two z-scores together. And if you look at the other pairs of z-scores, I have a positive and a negative. And that is the same pattern all the way through. So every time I do that multiplication of those two z-scores, I'm going to get a negative every single time. So let's look again at our formula And we see again as we look at our numerator that we're going to sum all those up, and when we do so we're going to get a negative 6.00, dividing again by our total n, our pairs of scores of 6, gives me a negative 1.00. Let's look at one more set of data. Now in this case I have chosen random numbers for all of my scores. So in set 1 these numbers are simply taken at random, just as these numbers in set 2 are taken at random. So almost by definition there is no relationship between these two sets of numbers. So let's take a look at the z-scores of these two sets of numbers and what happens when I multiply the z-scores together. So again, the very first number, the first z value is a positive 0.39, but again there's no way to predict what that was going to be, just as there's no way to predict what this z value would be. So in this case we have two z values. When I multiply them together I see it's a positive multiplied by negative. So I get a negative. But the next one I happen to have two negative z-scores, which of course when those are multiplied together I'm going to get a positive. And again it's just haphazard what's happening here, and we begin to see that we have, okay, here's a negative, but the next one's a positive. Next one's a negative. So they're kind of balancing out just because of the randomness of these particular set of scores. So when I, again, going back to the formula, looking at my numerator, as I sum all these up, I'm getting a value that is rather close to 0. So it's a negative 0.45. I divide that by the pairs of scores at 6. I don't get exactly 0 because these were, after all, random numbers, but it's very close to 0. I have no relationship whatsoever between these two sets of scores, hence my Pearson R, which is very, very close to 0. So I hope this gives you a really good sense of what's going on here. I also hope you see just how easy it is to compute a Pearson R given the z-score method. The computation, especially given the power of Excel, is almost trivial. But again, this all assumes that you understand how we get to a set of z-scores. I think this really demonstrates the building block nature of statistics. Of course, I hope these examples also really make you feel prepared to dive right in to Excel and begin to compute your own Pearson R. One of the most important applications of correlation in education is in the area of testing and measurement, and in particular in determining the reliability of our measurements. I think a good synonym for reliability is consistency. The idea is if you were to give me a test and then ask me to retake the test, you would expect that my score the second time would be very close to my score the first time. Another important principle in testing and measurement is validity, which is simply whether or not a test is actually measuring what it is designed to measure. For example, if I were to give you a test that I thought was going to determine if you knew how to calculate z-scores, but in fact it really only determines if you know how to compute standard deviations, you would say that that is not a valid test of your ability to show me that you know how to calculate z-scores. So a good analogy for showing what we mean by this relationship between reliability and validity is this idea of shooting at a target. So you can see in this first target, I say it's reliable but not valid because all of the arrows or darts are all clustered together. So if I were to take the test and retake the test, I get a very consistent score every single time. But obviously it's not actually testing me on that particular objective. So it's reliable, but it's not valid. In the second example, you can see that my arrows or darts are all over the board. So every time I take the test, it's again kind of a random guess what my test score is going to be. Sometimes it's high, sometimes it's low. So it's certainly not reliable. And in the world of testing and measurement, if it's not reliable, it cannot be valid. So obviously what we're looking for are tests where if I were to take the test and retake the test, my scores are consistent and they are also on target. They are actually measuring what the objective of the test actually is. Well, I hope this presentation gave you a good introduction to correlational statistics. I think we need to have a good reminder at this point that a strong correlation in no way implies causation. You can make no statements regarding cause and effect simply on the basis of correlations. And I hope this presentation gave you a good orientation to how to actually compute a Pearson R. The next step obviously is to head over to Excel and begin to compute a Pearson R for ourselves. Until next time.